Welcome to today's example for hypothesis test of the mean. I think we could get by with just one example, but I'd really like to do these two examples to compare them and point out why we do hypothesis test. Because we're going to do two very similar and related examples, I'm going to try to color code things. I'll start off with some black to do this. First off, it is a hypothesis test because it says level of 0.05. So we're going to go through those 6 steps that we've been talking about. The parameter that we're testing this time is the mean. It says the mean is not 380 grams. It doesn't mention proportions. And again, usually mean questions will use the word mean or average. So instead of P, we're using mu. Still going to look at what number I'm testing it against. We're supposed to have 380 grams. You do not have to put units in the hypotheses. I personally find it helpful when I go to do my interpretation, so I try to remember to do it. And of course, not every mean question has units, but most do. And then how are we testing it? They're supposed to have 380 grams, so that's equal to 380. And then the alternative would be not equal to. Since the company is saying that each box has 380 grams, the claim is the null. Step 2 is the picture. Now this time, much like with confidence intervals, we're still going to draw a bell-shaped picture with a mean at 0, but it's not the standard normal that we use back with proportions. Just like with confidence intervals, this is the t-distribution, or the student's t-distribution. So the picture is going to look the same, but just note that there's something a little different, which will come into play in just a minute. Because the alternative is not equal to, we have two-tailed test. And as we talked about in the last example, when it's two-tailed, you got to pick one and label it. I'll label the left, and what I'm going to label it as T, because it is the t-distribution, not the z-distribution that we did before. So that's really the only difference in the picture, is using a t instead of a z. But everything else stays the same. And for purposes that will hopefully make sense later on, I'm going to draw a line. Normally you would not do this. And I'm going to switch colors. And we're going to look at part A. So we're supposed to be, for step 3, calculating the standardized test statistic. And we should go back and write that formula down. Since it's the t-distribution, the standardized test statistic is called t, no longer z. And its formula is this. At least the numerator should look vaguely familiar to the numerator of the proportion test statistic, because remember it was p hat minus p, that is, it was statistic minus parameter, and that's exactly what we have in the numerator. The denominators are similar, but that's a little harder to see, so I'll just say trust me on that. So we have that for our formula that we need to use for step 3. X bar for part A, the mean from the sample was 379.1 minus mu, the parameter always comes from the hypotheses, so it is 380, divided by S from the sample is 4.2, divided by the square root of 50. So we had, and now I've forgotten, 379.1. Divided by parentheses for the denominator, and it was 4.9, I think. 4.2. Divided by the square root of 50. Note that you're going to end up 50. you're going to end up with two closed parentheses at the end, one to close the square root and one to close the denominator. Sometimes that confuses students. So we have negative 1.52. And again, since it was two-tailed, I'll take note of the fact that I actually did get the t on the correct side this time, since it is a negative, so I don't have to move it. Step 4 is the p-value. Since it is two-tailed, we need to multiply by 2 or double it to get both tails. And since my test statistic is on the left, I don't need the complement rule. We do, however, get a new Excel command, the t.dist. This should be no surprise since we use norm.s.dist. Now we're going to use t.dist. We'll cell reference the negative 1.52. We will also need to tell it, like we did with t.m, the degrees of freedom, which is still n-1, or in this case 49. And like most of our dist questions, we'll need to tell it true. And as before, you do need to cell reference because it was not exactly negative 1.52. So our p-value is 0.1361. So step 5, our decision. So my level of significance was 0.05. 0.1361 is not less than 0.05. So we fail to reject the null. And then my decision starts very much like it did before. Last time I said proportion, but here we're not doing proportions, we're doing mean. So I'm going to use the word mean. So that the mean, and then you need to tell me what you, for lack of a better word, measured. We were measuring the mass of cereal in each box. So the mean mass of cereal, and then the all statement in all boxes could be, and since it's failed to reject, it could be the null, so it could be 380 grams. One of the reasons why I like putting the units in the hypotheses is it helps me remember to stick the grams after the 380 here at the interpretation, because they are required in the interpretation. We have those same 4 possibilities. Oh, and I think I forgot. No, I did. We have those same 4 possibilities for how we can interpret in the context of the claim. And since the null was the claim, and since we failed to reject the claim could be true. Now, this question didn't address using the complement rule, but if it was on the right side, you would need the complement rule. If it was one-tailed, you wouldn't need to double, but all that stuff we saw back with proportions. The main new thing here was a new formula for the standardized test statistic and the new Excel command t.dist for the p-value. Everything else is very much the same as what we did with proportions. I did want to, as I said, do this part B just to make a comparison. So let's look at part B. Notice what happened is we have a new sample, which means that steps 1 and 2 are not going to change. And that's why I did those in a different color, and that's why I drew the line, because I knew those were going to be the same no matter whether we were talking about part A and part B. But we need to start over with step 3. So I'll draw another line. So for part B, we still have the same formula, but this time because we have a new sample, X bar and S are going to change. It turns out N stays the same, but N could change. So X bar for part B is 379.6, S is 1.2. Since my hypotheses didn't change, mu is not going to change. It's still 380, just straight from the hypotheses. So I always forget these numbers. 379.6 minus 380 is 380 divided by 1.2 divided by the square root of 50. So we get negative 2.36. Now, just to take note, it is, while it is different than the one we got with part A, it is still on the left. So that t being on the left is still good. So to find my p-value, and I'll label this as step 3. So to find my p-value, we still need to double because it's two-tailed, but we don't need the complement rule because it's not on the right. Still have 49 degrees of freedom. Oh, that was nice. We get 0.0225. If we can get back to the problem. Now, for the first time, 0.0225, and my screen's not, there we go, 0.0225 is less than the level of significance. So for step 5, our decision is to reject the null. And since this is the first time we've seen this, I'll point out what we're saying is that H1 is true. And this is not wishy-washy. This is confident. So again, we start with our significance level. And we're talking about mean. And again, the thing that we measured was the mass of all cereal boxes. And this time it's not could be. This is not wishy-washy. It is. And since we're saying H1 is true, H1 doesn't say actually is, it says is not 380 grams. And then since the claim was the null, and we rejected the null, we are saying that the claim is false or the claim is not true. And again, that goes back to those 4 choices in that box that I gave you. And again, you can say not true or false. The reason I like to do both of these examples is to talk about the importance of standard deviation. In the first example, in part A, the mean came out to be 379.1. And the real question is 379.1 close enough to 380 to say that the machine is working? And what we learned is that in part A, yes, it is close enough. So you would think in part B, with a mean of 379.6, that's even closer to 380. So if 379.1 was close enough, 379.6 has to be close enough. But it turned out that wasn't true. 379.6 was not close enough because the standard deviation was so much smaller. Things are much more compact at that second one. So just an interesting reason why standard deviation is important, and also this idea of, you know, hypothesis test is telling you what is close enough, and it's doing it in a mathematical way. This is the only example I have for 8-2. If you have questions, as always, please contact your instructor.